Good. Welcome, period 8. You got to make up the half day before Thanksgiving. Good. Woo. I will now introduce you to a powerful new technique. You're going to run the camera as I move to the thing? Good. All right. A powerful new technique called the principle of mathematical induction. This is a way of proving very, very low-level claims about numbers. And this is not actually just like this is not actually just like another little like trick. This is actually like built into the very definitions of the natural numbers themselves. More on that if you take logic as a senior. All right. So take, whoa, what happened? You moved.
He found a desk that's facing you.
Cool. Okay, so take this thing that we just did on the backboard. Do you consider that to be a proof? Kind of. Karen, can you close the blinds? So I guess here's how I feel about this. Personally, my sort of opinion about this is it's like decent. Yeah, good. So I would call what we did over here on this board, I would call this a discovery. In other words, and I don't want to like downgrade the role of discovery in mathematics. It's like pretty important. We discovered via this process what the formula was for the sum of the squares. But notice how there were all these like pesky like dots in here, right? This is sort of me just kind of waving my hands and saying like, just trust me, man. Everything continues just fine, just like this. But if you really want to prove something, then about numbers, what you need to do is sort of like prove it for real. Okay, how are we going to do this? Well, one thing we could note is that. Okay, so here's what I want to prove. What I want to prove is that that this formula is true, right? So I want to prove that 1 plus 4 plus 9 plus 16 all the way up to n squared. I want to prove that this is n plus 1, 2n plus 1 over 6. But I don't want to prove this for a particular number. What I really want to prove is that this is true for all possible numbers. In other words, I want to prove that this is just like a property that numbers have. That when I add up the squares up to that number, then this is the formula that I get. All right, well, one thing we might do is we just might start just checking it. So like try when n equals 1. If when n equals 1, what do you get on the left-hand side?
1 times 2 plus 3 is 6.
Wait, on the left-hand side you get? 1. Just 1. On the right-hand side you get? 1 plus, times 2, thank you, times 3. So that it also just, it like works, right? They are equal. Okay, and so actually for purposes of comparing what's going on here, I can maybe nickname this expression on the left-hand side. I can nickname it like a sub n. In other words, let a sub n be the sum of the first n squares. And this formula on the right-hand side, I can nickname b sub n. All right. And so what I really want to prove, is that the formula a sub n is always equal to the formula b sub n for all n. That's what I want to prove. And what we started just doing is like checking it, right? So let's check it when a is 1. Well, when a is 1, as you guys told me, I get 1. And when b is 1, I also get 1. In other words, indeed it is true that a sub 1 equals b sub 1. Check. All right, and if I was just being very sort of naive about this, I could just check it again, right? What is a sub 2? What is the sum of the first two terms? 5. And how about b sub 2? What happens to the right-hand side if I just plug the number 2 in? Okay, I get 2 times 3 times 5 over 6, so this is also 5. Okay, And so again, the formula works when n is 1, and the formula works when n is 2. Okay, but now I'm sort of like have committed myself to just checking this like forever, right? And that seems impossible. I don't want to just keep checking forever, that's lame. I want to show somehow that this is true for every single possible n. And here's where we use the principle of mathematical induction. And the principle of mathematical induction says, principle of mathematical induction says that if you have some kind of property that a number has, so if some number, if you can show that 0 has that property, and if whenever, for any possible k, if the number k has that property, then the next number also has that property. If that's true, now I'm going to just giant brackets around this, then all numbers have that property.
What is the upside down V?
That's for all. Didn't we use that already last week?
For all.
Yeah. This is for all.
Happened to the tip.
For all.
What's the carrot?
Upside down V. No. Oh, this is and. Sorry. I can just write and. That was your question?
Yeah.
And that's the and symbol. Didn't Piper teach that? No.
Yes,
no?
It's an ampersand.
Piper uses ampersand. Yeah, this is another variant. Okay. Good. So yeah. So wait, like follow the logic. Principle of mathematical induction says, if you have some property, and you can show that 0 has that property, and if whenever a number has the property, the next number has the property too, then it just kind of goes on forever, like dominoes, right? The next number has the property, and the next one does, and the next one does, and the next one does, and the next one does. Then all numbers have that property. And actually, this is true for every possible property. This is the principle of mathematical induction. Okay, let's watch it in action. Also, are you monitoring whether I'm in frame or not?
Wait, are we going to prove this?
Am I?
You?
Okay, so you prove, no, we are not going to prove this. This is an axiom of numbers. This is just like unprovable. Okay. So anyway, this checking that it works, this is sometimes called the base case. And now what we're going to do is we're going to make our inductive hypothesis. And our inductive hypothesis is to suppose that this formula works for k. Okay, so basically you're going to take an arbitrary k, so take an arbitrary k, and suppose that a sub k equals b sub k. In other words, what we're doing right now is we are just going to assume temporarily that this formula that we're trying to prove, that it works for k. And then, what am I going to do after that?
Do it for k plus 1.
Prove, or maybe I'll say show, yeah, but by do it, like demonstrate that it works, right? Show that a sub k plus 1 equals b sub k plus 1. On the assumption that it's true when n equals k, if from that assumption I can conclude that it works for k plus 1, then it must be the case that it works for every single number. Okay, let's do it. All right, how can I show that it works how can I show this fact? Well, basically it's just like a trig identity, you just kind of start, right? So what is a sub k plus 1, after all, by definition?
It's like
It's like 1 plus, people are mumbling it, 4 plus 9 plus, how far out do I go? Yeah, so k squared plus k plus 1 squared. So here I'm just sort of like starting the proof by writing out what a sub k plus 1 is. And Sam Felsenfeld said something already which should be obvious to all of you. What is that?
It's just a sub k plus 1 squared.
Yeah. A sub k is the sum of all of these up to, so this is just a sub k basically, right? Okay, so far I have that a sub k plus 1 is just a sub k plus the like additional thing, right? Alright, and I am trying to prove that this is true, or I need to show that this is equal to b sub k plus 1. Well, I get to use my assumption. And that assumption is going to be like crucial, right? Here, I have supposed that a sub k equals b sub k. So on the that's called my inductive hypothesis. So on the assumption that that's true, like replace a sub k with b sub k. You guys with me?
Yeah.
Okay, cool. So young, can you raise it? Okay, so what we actually have is that a sub k plus 1 is b sub k plus k plus 1 squared. And I'm allowed to do that because I've assumed that a sub k and b sub k are the same in order for this step. You guys with me?
Yes.
Okay, now what is b sub k by definition?
That thing.
That thing, right? It's just like k plus 1, 2k plus 1 over 6 plus k plus 1 squared. All right, well this is just algebra now, right? All right, you take it from here. Simplify all that. You guys with me? I think it just works out. I recommend factoring out a k plus 1, I think. What's up? You don't have to see, it's all on your brain. Guys with me?
Yeah.
This part's just like algebra now, right? You cool? Yeah, so yeah, throw in a little like 6 over 6 to get a common denominator.
What?
2k plus 3.
Where did the 6 go?
What is it from? Right. 2k squared plus 7k plus 6.
Okay.
You don't need that. I think it's easier just to show it this way.
Okay, does that factor? 2k squared plus 7k plus 6?
Yeah.
Yeah, what does it factor as?
2k plus 3, k plus 6.
Yeah, k plus, exactly, yeah. This is 2k, what is it?
2k plus 3 and k plus 6.
K plus, no, it should be k plus 2 times 2k plus 3, yeah? Okay, and you may or may not recognize that immediately, but that just is b sub k plus 1, right? Because after all, you could write this, what we have shown is that a sub k plus 1 is, if you wanted to be super fancy, you could write this as k plus 1 times, this k plus 2 is really like k plus 1 plus 1, With me? Are you moving the camera? Keep up with me? And 2k plus 3 is really like 2k plus 1 plus 1. Follow? All over 6. Okay, so what we have just done is we have just proven directly that a sub k plus 1 equals b sub k plus 1. Cool? And this proof used at a crucial moment our assumption that the formula worked for the previous number. In other words, what I have just done is I assumed that it worked for k, and I showed that it works for k plus 1. Okay, here comes the principle of mathematical induction in action. It says, yo, you showed directly that it works when k is 1. Okay? And you proved that whenever it works for the next number 2. Therefore, it works for 2.
All of them.
But also, whenever it works for the next number 2. So it must work for 3. And if it works for 3, it must work for 4, and blah, 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 blah. The principle of mathematical induction is the power to then say, therefore it works for all numbers. Get it? Okay, and so I insist that you write this. There's a sort of a magic sentence now that I want you to write, which summarizes the entire process. And so, what we have showed is, so now we're like concluding sentence. A sub 1 equals b sub 1, we showed that. And for any k whatsoever, on the assumption that the formula works for k, we proved that the formula works for k plus 1. We proved the conditional, right? Because we assumed that it worked for k, and we showed that it worked for k plus 1. So, by the principle of mathematical induction, we can now conclude that it works for all n. Does that make sense? Exactly what we're going to do. All right, Wild is right. Good. Okay, let's do one more. Yeah, let's go. So here we go. I'll give you a problem. 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus dot 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 all the way up to 1 over n times n plus 1. All right. We're going to do some real mathematics here in these last 7 minutes. What is this?
It's like a series.
It is a series. Play around for a minute and figure out what the formula should be. I'm going to move this over here. Too late.
Oh my god. Ah!
We may have done this one for homework. No, don't do that.
Oh.
Ew.
No, that's not it.
Everyone, test. It's not harmonic.
It's like the harmonic with your
Yeah.
No, not even that. Harmonic
Okay,
with your
how are you going to figure out this pattern if you have no reason to believe that it fits any one of the previous patterns?
Make a sequence of the partials.
Yeah, you just like conjecture, right? What's the sum of the first 1 terms? 1/2. What's the sum of the first 2 terms? 1/2 plus 1/6, which is
Oh my god.
good. Okay, I'm just doing it. There's nothing. I'm not doing anything deep here. What's the sum of the first 3 terms? 2/3 plus 1/12. 9/12. That's 3/4. Should we do one more, or are you starting to feel the answer? Sum of the first 4 terms, 3/4 plus, the next one would be 1/20th, right? And he's doing it already. It's 16/20th, it's 4/5. All right, do you have a conjecture for the sum of the first n terms? N over n plus 1. All right, now previously, as in last week, we just had to hopelessly take it on faith that we have found the correct formula, right? But now here I am intentionally splitting up the mathematical process into one of discovery and one of proof. I now know what my theorem is, and now I have to prove that that theorem is true. Okay, how can we prove that this theorem is true?
Prove that it works for K.
Yeah, we have to do induction, right? So prove that this works for all n. All right, and I recommend doing what we did before. Nickname this whole left-hand side of the equation a sub n, and nickname the right-hand side b sub n, just so it's like easy to refer to. That's just like a kind of organizational step. All right, and you basically need to do two things: the base case and the inductive case. What's the base case?
Do like 1.
Yeah, you just check it for n equals 1. So in the base case, check for n equals 1. When n is 1, what do you get?
1/2.
Yeah, a sub 1. It's like you just stop when that's a 1. Well, that's like the first term, right? So that's 1/2. What's b sub 1?
1/2.
1/2.
Woohoo!
Okay, so it works. A sub 1 does equal b sub 1. All right, now that you've checked that it works for the base case, now we make the inductive hypothesis. And the inductive hypothesis is, what is it?
Assume A sub K equals B sub K.
Yep.
And take an arbitrary K.
Yeah, you can kind of, you sort of like, you know, for just a generic K, that's kind of the idea there, right? For just a generic K, or an arbitrary K, most people don't even write that step, just assume that A sub K equals B sub K. And then, what do we need to show?
Prove that it works for A sub K equals 1.
Yup, go, do it right now, it takes like 1 minute. Good, because that's all we have, so go. Oh no, we have like 3 minutes, perfect.
It would be like n factorial, no, k factorial.
It was.
So I told my wife to make sure my baby plays with polyhedral all day long.
Okay.
Totally.
Are you proud of your child?
No, she hasn't really done much yet, she's just like, oops. Perhaps.
Not too different. Wow. Here, you guys have
It's like pretty fast, right? Once you just start, you're like, oh, fast. Because what is a sub k plus 1? It's like 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. All the way up to 1 over, I like to use k just to distinguish, but it doesn't matter. If you want to use n, it's fine. But then you go until until n is k plus 1, right? I find it awkward to, I like to use a different letter because it just makes it, then you can say things like, let n be k plus 1. You know what I'm saying? Is that in frame? It is. All right, and now, of course, what is this? What is a sub k plus 1? It's essentially just
A sub K plus
yeah,
1 over that.
yeah. It's just a sub k plus that last extra term you added. You with me?
Yes, I know what you're saying.
And now, yeah, by assumption, a sub k is b sub k. So I think it's nice to write it like this, just for clarity. And then b sub k is just our shorthand for k over k plus 1. Yeah, I think if you just do a common denominator, that's the simplest, right? Yeah. So this is k times k plus 2 plus 1. So that's k squared plus 2k plus 1. Okay, final answer is
K plus 1 over K plus 2.
k plus 1 over k plus 2, and that just is, by definition, b sub k plus 1. Cool, cool? Alright, final magic sentence.
A1 equals B1.
A1 equals b1,
And for all K.
and for all possible k, because the k we assumed was generic, assuming that a sub k equals b sub k implies that a sub k plus 1 equals b sub k plus 1.
Magic.
So, this is just summarizing what we did. So, by the principle of mathematical induction, a sub n equals b sub n for all n. Good?
Good.
Great.
Great.
Probably some kind of quiz next class on sequences and series. FY. Yeah.
They have it first because
Yeah.
What?
I thought they have to take it first this time.
I never said that.
Standing up.
Yeah, you did.
At some point, I'll give them some stuff first. Yeah.
Thank you.
Their parametric equations quiz is much harder. Oh, the magic sentence was out of frame. There it is. Woo woo! Okay, everyone say goodbye to period 8.